So today we're going to talk about the historical chemical significance, keywords, key people, key steps in the synthesis, the problems, concepts, takeaway themes and ideas, and future initiatives and possible undergraduate laboratory applications. So ultimately, we believe that the cause of this product resistance is based in God. Bacteria and archaea are the unicellular organisms that mainly produce B12 on Earth. The total synthesis of B12 was developed in 1972 by scientists at Harvard and PK Zurich in Switzerland, and Dr. Folkers in 1927 was able to discover and isolate the compound. So if we look at the history of B vitamins overall, we see B2 riboflavin was discovered in 1933. It was isolated. B6 pyridoxine in 1934 was discovered. In 1938, the active compound B6 was isolated. So Dr. Folkers and his team determined the structure of B6 pyroxidine, and in 1940, B5 was reported by Merck. So let's talk about some key people. So John G. White and Dorothy Hodgkin played a large role in discovering the X-ray crystallographic structure of vitamin B12. K. Bernhardt determined the partial synthesis of vitamin B12 from cobyric acid, and Robert Woodward and Albert Eschenmoser, they worked together to determine the total synthesis of vitamin B12, which they reported in 1972. So R.E. Woodward, one of my favorite scientists that I learned about while on my time in the field. R.E. Woodward, he determined the total synthesis of vitamin B12 and also other natural products such as quinine and cholesterol, and in 1965 he won the Nobel Prize. Albert Eschenmoser, who is actually still alive today in his 90s, worked with R.E. Woodward to determine the total synthesis, and he contributed to synthetic organic chemistry, and he won the Davy Medal. Dorothy Hodgkin was a really good X-ray crystallographer, and in 1964 she won the Nobel Prize. So, in terms of its significance, the reason why I chose B12 is because it has clinical significance in that it is used to treat acute cyanide poisoning. It's a popular topic in terms of nutrition, discussion, and energy. The total chemical synthesis of it is cool. And also, 6 Nobel Prizes were awarded directly and indirectly associated with vitamin B12. So in terms of treating acute cyanide poisoning, the reason why hydroxycobalamin is able to treat acute cyanide poisoning is because this hydroxide is displaced by a cyanide and it's passed out as cyanocobalamin, so it's harmless in terms of excretion. Now, the scientific name of what I'll be focusing on, the form of B12 I'll be focusing on, is cyanocobalamin. The metal center is cobalt. It also functions as a coenzyme, but this R group is 5-adenosyl, but it's different from the cyanide that's attached to the cyanocobalamin. There's a macrocyclic structure, which is a corin. It's similar to the porphyrin in heme. B12, like B and C vitamins, are water-soluble vitamins, and B12 is metabolized in the liver and excreted by the kidney. So animals store B12 in their liver and muscles, and some passes into their eggs and milk. So this is just showing you that you have 9 B vitamins, but the one we're going to focus on in this discussion is B12. So this piqued my curiosity. B12 as a coenzyme complements catalysis in several different ways. But if you were to generalize all of this, there is the stereospecific interchange of groups on adjacent carbons, all of these things, if you were to generalize all these instances. This interchange. In terms of nutritional benefits, it functions as a cofactor in DNA synthesis. It's a cofactor in fatty acid and amino acid metabolism. It's important in normal functioning of the nervous system, and it also functions in the maturation of developing red blood cells. So this is the coenzyme form, and this is the 5-adenosyl attached as the R group in this. So this is just showing you your side. You can have the cyanide, the hydroxyl, the methylcobalamin, or the adenosylcobalamin, which you have different R groups here attached. So, the synthesis of vitamin B12. As you see here, you have ring A, B, C, and D. Those are synthetic targets. You have the Kaiser-Smith condensation. You have cycle, addition, oxidation. All of these steps that you're seeing right here, I chose to briefly show these steps because these were the 38 steps I had to focus on in writing my paper. Yes. And this was Eschenmoser Variant. And it was started first before the Harvard Variant. The Harvard Variant was started in 1961. The Eschenmoser ETA Zurich Variant started in 1960. So here you see thionation, aminolysis. These are several reactions: ring opening, the RNA stirred reaction. This one is very interesting. In the process of me determining that the reaction that was just on the screen, in the process of me determining that, I was able to contact one of Woodward's former students and gave me insight into the mechanism that was occurring with the reaction. My favorite step, which I'll talk about later, the amino acid condensation. Thionation, sulfide contraction, a really interesting step. Aminolysis. You see the rings getting bigger and bigger. So we are forming the macroscopic structure that composes a large portion of vitamin B12. This is a very important step, which I'll talk about later. The complexation step, alkylation, reduction, esterification, reduction, and hydrolysis and aminolysis, and then the final step in terms of synthesizing cyanocobalamin. So let's talk about some key words that were like pinpoints I focused on as I studied the B12 reaction schema. So these are several words that stood out to me: homologation, recoring, aminolysis, thionation, methanolysis, the Woodward-Hoffman rules, and protection and deprotection. So homologation. This is primarily, the main idea I take away from this is this occurs when the repeated structural unit is increased, and in this schema, the repeated structural unit was the methylene or the CH2. Excuse me. Now we have the macrocycle, which composes a large portion of the vitamin B12 molecule, and this is a porphyrin, which is different from the porphyrin. One difference is the porphyrin is larger. Now we have aminolysis, which was a step that was repeated in the total schema of vitamin B12, and you can see the difference that you have occurring here. You have an alkylated amine being converted to an overall amide molecule. And then you have thionation. The main thing to take note of here is you have a carbonyl being converted to a thiocarbonyl, in which you have the oxygen in the carbonyl being converted to a sulfur. And then you have methanolysis, in which you have methanol. This is just showing you an example from the schema in which you have methanolysis occurring. But methanolysis in general is when you have methanol functioning as a nucleophile, similar to how water functions as a nucleophile in hydrolysis. Now, the Woodward-Hoffman rules. One thing to take away from Woodward-Hoffman rules is it gives us insight into the mechanisms of some of the reactions in the schema. And also, it tells us that reactions, whenever possible, proceed through aromatic transition states. So if we look at this mechanism, if you go in the forward direction, you see protection with ethylene glycol, and if you go in the reverse direction, you see deprotection. So key steps in the synthesis. Yes. Yes. Lord of the Rings. 12, almost like Lord of the Rings. Yeah. It's almost as if they were being told, you shall not synthesize, but they still did. So, it took them 12 years, but they still did it. Now, as I mentioned already, you have two different variants: 1960 variant, which was started at ETH Zurich, and the 1961 variant, which was done at Harvard. It was collaboratively pursued in 1965. And the interesting thing to note is it required the work of 91 postdoctoral fellows and 12 PhD students from, I think, 19 different nations. Now, As you see here, you have A, B, C, and D, and you have the chlorine macroscopic structure. Now, I chose to put this in the presentation because there are some similarities between the Woodward variant and the Eschenmoser variant, in that you have similar intermediates in which you have the cyanobromide, and then you have this dialdextrin, which is similar in Eschenmoser variant. So your similar reagents and intermediates both involve joining the rings, but the differences occur in the two different variants is that you have the closure, the cycloisomerization reaction occurring between rings A and B in the Harvard variant, whereas in the ETH variant you have ring closure at A and D. And this occurs by a photochemical process involving frequency of light. The stories of the rings. So I chose to work through the photosynthesis, study photosynthesis, and I picked out key steps that were my favorite from my studies of organic chemistry, and just it made a lot of sense to me in terms of the mechanism. So you have the Claisen-Smith condensation in which you had ethyl methyl ketone reacting with acetaldehyde, and then you had the ring opening and the fluorination step. All three of it stood out to me. Again, one thing to take note of in our synthesis of all 4 ring precursors to vitamin B12 is that all involve the first step being Claisen-Smith condensation, and you have thionation in this case. You have thioesterification and reductive decarbonylation by a metal catalyst, and Claisen-Smith condensation, and this step, as I mentioned, I got insights in this from Scott Schreiber, who was a professor who was a former student of R.B. Woodward. Now, my favorite example from the entire synthesis of vitamin B12 was the amino ester enamine condensation with a sulfide interaction using alkylated coupling. And as you can, if you look at this picture, you see that there's some differences in that this is written in German. Yes. It required me doing a little bit of translation by Google Translate in order to get what they were saying. But it was worth it because as I looked through it, I got more insight into what was happening mechanistically with the reaction in the schema. So some key problems that these people faced when they were synthesizing vitamin B12. The introduction of the metal center, cobalt, that was a challenge. They used cobalt chloride. The closure of the macrocyclic ring, which makes sense because the two different variants, the 1961 variant done at Harvard and the 1960 variant done at ETH Zurich, they close the ring in different ways at different places. The S differentiation, because if you look at cobaric acid, which was the synthetic target, if you look at cobaric acid, it has several different S groups, so you have to choose between whether you're going to protect one and then react the other, or deprotect one and then deal with the rest. You have the introduction of the methyl group at the bridges, specifically at ring A and B and between C and B, and then you had to restore the lost stereochemistry that occurred during the total reaction schema. So this is showing you the methyl groups at the bridges. How they approach these problems. So the main things that they did was they worked with each other, and they did an exhaustive study of the relationships between various isomer bioethers. And this was something that stood out to me. In all of this, it required them using every conceivable precaution in respect to purity of reagents, exclusion of oxygen and moisture, and they had to do this with the greatest possible speed. Talk about a tough synthesis. Huh? Can you imagine trying to do this in the lab over the semester? This would be really hard. Luckily, I didn't have to do it. Yeah. They used rigorous stoichiometric relationships, which makes a lot of sense because the reagents are expensive and introduced. Now, key concepts I want you to take away from this presentation. Now, you have condensation, contraction, convexation, elimination, reduction, and the implications of the Woodward-Hoffman rules. So in this example right here, you have condensation occurring, which basically is two molecules coming together and you result in the release of one. In this case, you have water being released. This right here is sulfide contraction, specifically Eschenmoser sulfide contraction, which is a key step in the joining of rings A and D and B and C in the macrocyclic structure for vitamin B12. Complexation, very important because cobalt plays a big role in determining the biochemistry of B12. Elimination was a key step. Reduction was also a key step. And the implications of the Woodman-Hoffman rules, it helped inform what will occur in different cytoisomerization reactions, specifically the 80 variant, which is the Harvard variant. Some takeaway themes and ideas. Science is collaborative. That was one of the things I recognized as I read through the research and looked through the literature. All of those people work together on this one specific research project. Research takes time. I am not sure whether I would want to work 12 years just to determine the structure of one vitamin. And future initiatives and studies. They also mentioned they want to know why cobalt was so effective as a metal center. I think more undergraduate applications can come about from this because you learn a lot. You basically cover like a series of reactions, some of which you studied in 2 semesters of organic chemistry, 1 and 2. And considering how vitamin B12 is mass-produced currently using microbial fermentation, I think more studies can be done in terms of efficiency and mass quantity studies. Now, this is what it took me a while to figure this out, to muddle through it, and figure out where can I possibly fit in an undergraduate laboratory application, or suggest one, I should say. Now, instead of suggesting going from hydroxycobalamin to cyanocobalamin, which is what takes place in the body, that's why they use hydroxycobalamin as a treatment for acute cyanide poisoning. Instead of suggesting that, I suggested that we convert cyanocobalamin to hydroxycobalamin. And the reason why I suggested that is because it would be a challenge to introduce or use cyanide due to its toxicity, even though it would be easy to do the reaction due to the toxicity of cyanide. That causes some concern, especially in undergraduate laboratory settings. However, cyanocobalamin, which is vitamin B12, which is easily accessible because it's found in different energy drinks and it's also found as chemical. It can be easily found, and hydroxycobalamin is used in medical settings, so it can be easily accessed. Also, cyanocobalamin is oxidized to hydroxycobalamin through the use of ascorbic acid, which I saw in this study right here, and also under a specific frequency of light, namely ultraviolet light, cyanocobalamin is converted to hydroxycobalamin. So there are many ways to do this, and we would be able to confirm that we carry out the reaction through the use of UV spectrometry. Specifically, if you look at the last peak of the different UV spectra, you see that cyanocobalamin has a third peak at 550 nanometers, but this one has a peak at 526. So different peaks would confirm to us that we achieved our goal in the reaction. Now, in conclusion, overall, in my opinion, the synthesis was elegant and elaborate because Harvard, initially when I started doing this research project for Chemist, I looked at the Woodward variant, but the Woodward variant had 70 steps. I chose not to use that one. I chose to use the Eschenmoser variant, which had 38 steps. Exhibited many types of reactions in inorganic and mainly organic chemistry, and it shows that hard work and collaboration with the right resources in science pays off. Yes, it requires persistence, single-minded, solitary hard work, and a belief in the importance of research problem. All those things are required by science. As I conclude, I would like to thank God, my family, my professors who are all present, and also my friends who are sitting here in the audience. Thank you.